Bandwidth for changelog is provided by Fastly. Learn more at fastly.com. We move fast and fix things here at changelog because of Rollbar. Check them out at rollbar.com. And we're hosted on Linode cloud servers. Head to linode.com/changelog. This episode is brought to you by DigitalOcean. DigitalOcean is the simplest cloud platform for developers and teams with products like Droplets, Spaces, Kubernetes, load balancers, block storage, and pre-built one-click apps. You can deploy, manage, and scale cloud applications faster and more efficiently on DigitalOcean. Whether you're running one virtual machine or 10,000, DigitalOcean makes managing your infrastructure way too easy. Head to do.co/changelog. Again, do.co/changelog.
Let's do it. It's go time.
Welcome to Go Time, a podcast featuring a diverse panel and special guests discussing cloud infrastructure, distributed systems, microservices, Kubernetes, Docker, and also Go. We record live every Tuesday at 3 p.m. Eastern, noon Pacific. Join the community that's live with us in real time during the show in the Go Time FM channel and Go for Slack. Follow us on Twitter, we're at GoTimeFM. Listen live at changelog.com/live or subscribe at changelog.com/GoTime. And now on to the show.
Well, hello and welcome to Go Time. I'm Matt Ryer. Today we're talking about concurrency. Go was designed with concurrency in mind, and that's why we have language primitives like goroutines, channels, wait groups, mutexes, these sorts of things. And they're very powerful when they're used correctly, but they can be very complicated if they're used unwisely. So helping me pick the threads today, I'm joined by Johnny Borsico. Hello, Johnny.
Hello, Matt.
How are you?
Oh, I'm here to pull some threads.
Good. Glad. Well, you don't have to pull them on your own. We're also joined by Jana B. Dogan. Hello, Jana.
Hello, hello.
How are you doing?
I'm just having my first coffee of the day.
Congratulations.
So I will be a bit sluggish, yeah.
Yeah, enjoy. And that's, there's another voice, if you've heard it or not. It's Roberto Clapis. Hello, Rob. How are you?
Hello, I'm fine. And since today is going to be a complicated subject, I'm going to tread lightly.
Ooh, oh, that is
nice.
Very nice to hear.
Off to a great start, I'd say. Thanks.
Okay, well, why don't we jump in? When C was designed in the 70s, the computers had like a single core, and they were much simpler than what we have now. And more modern machines have multiple cores, and so there's more potential for doing things at the same time, whatever that means. And so when Go was designed, of course, they knew this situation. And so that's why we have Go routines, and we have channels, and we have those other primitives. And Go is actually quite famous for concurrency. Actually, they become quite synonymous when you talk about languages out there. And do you think it deserves that credit that it gets?
I think it does. Actually, before using Go, I had been using Python for years. And at one point, I needed to solve a problem using all the 36 cores that I had available on a cluster on my university. And the pain of doing that with a language that wasn't designed with that in mind actually brought me to say, okay, what about learning a new language and maybe makes this easier? And with Go, it was, I think, 100 lines and I was done.
Wow.
I'm coming from a JVM background, and like every time we start this like large, process heavy type of stuff, I was always complaining that it's taking all of my, processing power. But it sounds like it's a good thing, right? Like rather than doing this manually. Yeah.
So for people that are new then to Go, I'll give a quick overview of some of the primitives and some of the language that we're probably going to use today, just to make sure that we kind of, know what we're talking about. So a Go routine you can think of like as another thread that's running. It's actually not a thread, but if you think of it as your main application runs and that's one thread, and if you want to do some work in the background, then you can spin up a Go routine to go and do some work. And actually, you can spin up quite a few of these Go routines to sort of go off and do their work, and they'll in theory do it as best they can with the hardware available to them. And then, of course, we have channels, which are communications allows communications between the goroutines. And so they're quite cool for, you can send and receive information in a safe way, because if you have these goroutines trying to access the same memory at the same time, you can run into problems. So they're the sorts of, I'd say, the generals of the two things. There's also the Go keyword, which is what kicks off a goroutine. So you can call a function and kick off a goroutine that way. So anyone that wants to learn more about this stuff, you can probably just search it in your favorite search engine, DuckDuckGo, or whichever one it is. So that's the overview done.
So I think it's important to also sort of talk about the kinds of things that might be sort of suitable for concurrency. So not every problem you're going to have requires, can even leverage concurrency. So usually we talk about, when we talk about, okay, if you write a program, when you talk about, okay, can this program be made to run concurrently, or parts of it be made to run concurrently, you're usually trying to identify what are the parts that are independent, that can be worked on independently of each other, right? So if you don't have any sort of dependency from one part of your task to the next, then these often are sort of cases where concurrency perhaps could be useful to you. So the goroutines themselves, you don't actually need the messaging mechanism of channels, to actually leverage concurrency in Go. Just the keyword Go will sort of get you started. The real kicker is, especially when beginners sort of start to understand, okay, how does this stuff work in Go? They usually find out, okay, well, it's a matter of basically your main program is itself a goroutine. And then if I'm going to kick off other goroutines, they need to somehow wait on one another, right? Your main goroutine needs to be able to wait on the work to be finished by the other goroutine or goroutines before your program can finish, right? This is where sort of the how do you string these things together, right? How do you properly leverage, right, concurrency in Go sort of becomes important. That's the part I think we could spend more time sort of out in the community, sort of doing more to educate beginners really on how to think and reason about concurrency in Go.
One thing that I really, really love about Go is that concurrency and parallelism are kind of separated, and you don't have to think about them. For example, when you use the HTTP package, every time your handler is going to be called, inside its own goroutine. But when you write the code, it feels synchronous. You know it's going to be an independent thread of execution, but you don't have to change your mindset to use it properly. It's not like you have to use async things or some different primitives. You just write your code for what you want to do, and it doesn't even have to run in parallel with other things, because if, for example, if you're running on a single core, it probably won't, and you just write it. And I mean, yeah, we probably should educate or put out some material to think about it and learn about it. But what I really love is that you can get started very easily and just write your synchronous code and you don't care.
Yeah, I think it's fairly also easy to, just migrate synchronous stuff to have more concurrency in it. The magic of Go is, I think, in select statements, and people have been complaining that it's actually not that easy to understand the behavior of select, but otherwise it's just like looks really readable and, really like there's no magic. And like this is one of the, I think, languages I feel more comfortable writing more concurrent code, and like other people just going through and like understanding what I'm doing. So Go is definitely currently my best tool probably for concurrency.
Yeah, I agree with you about the select statement. When you really get that right, can be extremely powerful. And the common way that I've used it recently a lot is checking for the context to be finished. So if I've got some work I'm doing in a loop, I'll have a little check somewhere, perhaps with a select block, that will just basically check if that context has been cancelled or not, allowing me to interrupt the work and exit somewhat gracefully if it's cancelled. And that's quite nice when you wire that up with the HTTP request context as well, because then you essentially, if the user cancels the request in the browser, in theory, that is going to stop the work that you were doing in order to prepare their request. And whatever saving that gets you, I don't know, but it's just very satisfying to know that that's what it's doing.
Do you feel like Go can do more out-of-the-box things with context? Like, I feel like there's a lot of boilerplate. You need to make sure that, the context is not canceled, there's no timeout and whatever. Do you feel like, is there any place that, there can be some improvements? Maybe there could be like certain features of select that automatically handles some cases or whatever. I'm just brainstorming right now, to be honest.
Yeah, I don't know. That's actually a really interesting question. I wondered whether having context just part of the language. And this is kind of a non-Go thing because Go likes to be very explicit all the time. But I could imagine there's always a context around and you can always cancel it and functions and things will get cancelled in the same way. You could almost imagine that. It's a bit like how exceptions probably work the opposite way in other languages. So I'm not sure it would get much support, but sometimes I do find myself just passing the context into every method, just everything, because even potentially my logging has need for a context. And so in that case, so does everything. I'd like to not do that as much. But again, it's explicit and you can't call that method without it.
I hope that just automagic context doesn't become a thing. I like to know when I start a Go routine, how and when it ends. Let's take an example. I acquire a mutex and I defer the release of that mutex. And that is fine. And then I change a little bit of state and then I do something else. And if I encounter an error, I want to be able to, for example, roll back what I've done so far. You can't always defer that. So sometimes when you write like transactional code, you want to be sure that you will not be aborted. Unless the program panics, but in that case, nothing will be committed. You really want to know how you exit. I would really like to know when code that I'm writing gets interrupted. And I want to be in control on when that happens and how. So if a context gets cancellated, I want to have a chance to say, okay, then roll back what I started doing.
Yeah, that's a fair point. One of the nice things about the select block is that it is actually a block. There's a case, there's then code that runs in certain conditions. So you do actually have that opportunity that you described to be able to go and do some kind of tidy up or some cleanup. And it is explicit.
Yeah.
Yeah. So it's interesting you mentioned you want to know when it ends. Has anybody got any techniques of how you can find out when a Go routine has finished?
I think that it doesn't matter how, but you should always know. I mean, I've seen so many programs and so many projects just become unmaintainable because they were just pinning up Go routines and let them run without handling their shutdown, graceful shutdown. Has this been someone else's experience too?
Well, they all shut down when your program ends, right?
Hopefully.
So you crash programs.
Otherwise you have a problem.
Yeah.
You know that there's a strategy of crashing programs once in a while, to kind of release that type of resources. So that's a fair point.
Yeah.
Just reboot it. I
wonder even why do we have a garbage collector? You run out of memory, just exit.
Yeah, restart.
That's what PHP is.
So to kind of address your question of do we know or can we know when the Go routine is done? I don't think there's any sort of a life cycle event or anything like that you can attach to know when a Go routine ends. What you typically do, however, is that this is where sort of the communication aspects of things start to emerge, right? So for example, if you know you're in your main Go routine that you'd like to know when another Go routine that you spun off has done doing its work and you want to wait for it, right? We have mechanisms in the language, like a wait group, for example, would be a great way to actually basically block until the other Go routine is done and then you're able to sort of move forward kind of thing. And this is also where channels come into play, right? So if the Go routine you spin off to go do some work, and if you can, when you initialize that, if you can pass some sort of a channel to receive some sort of communication back when that work is done, either your main Go routine or some other Go routine that needs to know about that event can actually be notified, right? So this is where that communication channel, right? No pun intended. This is where that communication sort of channel is necessary for you to kind of know basically the state at what point, right, of the work that you spun off in a Go routine. What's the state of that? Is it done? Is it finished? And there's lots of other different ways as well. You can sort of enable that sort of that communication, but there's no direct way of saying, hey, did this Go routine finish, right? You kind of need some instrumentation around that.
You mentioned about the life cycle, and there's literally no APIs for that. And, it's by design, just keeping everything more compact and simple to the user. But in the last couple of years that I've personally came to a lot of cases where I really wanted to, execute the limitation in some ways, or wanted to pin certain Go routines or the underlying OS threads to some, processors and so on. Did you ever had any troubles in the scope of this what do you feel about like the Go is very, very simple when it comes to like, execute. It just kind of handles it all and like encapsulates the problem from you, but it kind of limits the user in a way. What is your take on that?
I think it does in kind of a good way. So for some things, the layer it gives you allows you to build better abstraction on top. For example, group, which is a thing that I use everywhere, because when you cancel the context, it's immediate to know when everything has ended and propagate the shutdown. But at the same time, if you want to go lower, as you say, for example, at one point you want to drop your privileges. So if you want one goroutine to say, okay, this program is running a root, shall not be root anymore. Dropping privileges is still broken and has been broken for 9 years because it's racy, has problems. Go doesn't give you that fine-grained control on the underlying threads or like pinning on a certain core, for example, for graphics. The only way to do that now is from the main function, say, okay, pin me on this OS thread forever, and I'm going to be the one that draws. And that's clunky.
Yeah, true. And like with Numa and all these like new ways of like actually like, controlling the scheduling, Linux kernel have this new capability called Numa. You can pin yourself to like certain processors or like certain group of processors. And people do this like for this like fine-grained optimizations because you know more about like the task, whatever you're running, and just grouping things together, whatever, it just makes sense. And I've been experimentally using Go for this purpose, but it's been such a hard topic. All you can do is just lock yourself to the OS thread, and like you have some control over the OS thread through some C libraries, and that's kind of funny.
I think it was the Ristretto authors that said that they needed a thread local storage, but Go doesn't offer you that, so they used sync pool, which is lossy, and still decided they were good with that because lossy was better than trying to share stuff with other threads. I guess when you get that far, you might be using something wrong.
True.
To be fair, they did say that there was actively use of some form of thread local storage under the hood, but it wasn't accessible to you as the user of the language.
Yes, that's why they did it.
There are actually some people who are abusing that underlying storage, and I've seen some companies doing like some automagical instrumentation based on that, like some sort of like execution tracing type of thing. And it's very controversial, and of course, like not recommended, but people are just reverse engineering and like hijacking that, which is scary.
How often do you think about internal tooling? I'm talking about the back office apps, the tool the customer service team uses to access your databases, the S3 uploader you built last year for the marketing team, that quick Firebase admin panel that lets you monitor key KPIs, and maybe even the tool that your data science team had together so they can provide custom ad spend insights. Literally every line of business relies upon internal tooling, but if I'm being honest, I don't know many engineers out there who enjoy building internal tools, let alone getting them excited about maintaining or even supporting them. And this is where Retool comes in. Companies like DoorDash, Brex, Plaid, and even Amazon, they use Retool to build internal tooling super fast. The idea is that almost all internal tools look the same. They're made of tables, drop-downs, buttons, text inputs, and Retool gives you a point, click, drag and drop interface that makes it super simple to build these types of interfaces in hours, not days. Retool connects to any database or API, for example, to pull data from Postgres. Just write a SQL query and drag and drop a table onto the canvas. And if you want to search across those fields, add a search input bar and update your query, save it, share it. It's too easy. Retool is built by engineers, explicitly for engineers. And for those concerned about data security, Retool can even be set up on-premise in about 15 minutes using Docker, Kubernetes, or Heroku. Learn more and try it free at retool.com/changelog. Again, retool.com/changelog.
So what about some other packages then in Go that we have? for when it comes to working in concurrent ways. Thinking specifically about the sync package. Sync once is a very helpful little utility. Essentially, you give it a function and it guarantees that that function will only be called once. And so it's very useful in a web context if you've got a handler that's going to do some initialization work up front, and you might want to defer that until the first time it's called. Then you put it inside the handler itself, but of course, since every request gets its own Go routine in Go, it's possible that two requests could come in at the exact same time, spin up two Go routines, and they both try and do that initialization, or they're checking for nil or whatever they're doing, and they'll sort of step on each other's toes, and you can use sync once to protect against things like that. What happens is the first one that gets there runs the function, and all the rest will wait until that function's completed, and then they'll unblock and continue. So really useful, very practical. It's such a great utility, but there are some other lower level ones too, aren't there?
Yeah, like sync map, which I think is the most misused single structure in the entire Go standard library.
Really?
Yeah, because people assume it's just thread safe hash map. It's not. I think it's a thread safe hash map is a map with a mutex. That's about it. The sync map is actually to reduce cache contention. So I've seen a lot of people plumbing it everywhere. They needed a sync map, but actually what they needed was just a map with some protection on top. And sync map is useful if you start noticing that you content caches too much and you have a lot more reads and writes. But I think that's about it. And it's even written, don't use this. Or even sync atomic. It's specifically written, don't be smart.
Yeah, I think it's the name. It's just like it says sync map. So I think it's just not very self-descriptive, right? Like that's the main reason. Because in the Go doc, it explicitly says, hey, for most of the time, you actually need a plain, Go map instead. But the name just doesn't suggest that. It should have been called maybe sync dot, like some cache, whatever, magic, whatever map.
So for those listening, the guidance there is to basically just use a mutex, right, to protect access to your maps, right? Is that what you're saying, Rob?
Yeah, basically that. And until you realize your mutex is the problem, don't switch to something else.
So that's an interesting thing then. So Johnny, could you just tell us, what do you mean by a map and a mutex? How does that actually work?
Right. So by default, your regular good old map, right, the stuff you'd create in your plain Jane Go code, is not safe for concurrent access. So you could have sort of multiple Go routines trying to write to the same key at the same time, that kind of thing. For reads, it's okay, but typically when you want to basically limit the number of Go routines that basically are either writing in or reading from your map, to just one at a time, right? So that's where your mutex, short for mutual exclusion, that's where that comes in. So basically it guarantees that only one of your Go routines is going to be accessing or mutating something about your map at any one time. So what we've been talking about basically is that, okay, does the sync package is map type? Does it give this out of the box? So basically to echo Jana is basically that, well, it's named like it should be, but it's not. Like, you should really be using like a regular map, but introduce a mutex to deal with that possibility of contention.
Yeah, thank you. And so, if you want to access this map that Johnny was talking about, you lock the mutex, then you do your accessing, and then you unlock it when you're finished. And if other things try and lock that same mutex while you've got it locked, they'll then wait for you to unlock. So they are synchronization points, and they do create contention. I mean, we're saying that we have this concurrent program, but not at these points. At these points, it's not concurrent. You have to all come here and wait for some reason. Yeah, and it can get tricky to think about.
I want just to annoy you. You should lock the mutex, defer unlock, and then access the map.
Ooh, let's talk about defer. Matt, you've been wanting to talk about defer forever.
I love defer. I genuinely am trying to do an entire episode on defer, but I think we just have to do it at the end of the season, don't we? We can't do it before the end. It has to be the final episode.
So with defer, the interesting bit, I think there have been a lot of performance improvements in defer recently. It used to be, I remember once upon a time using defer, and there were some benchmarks that were floating out there in the past, basically showing that defer, basically you incurred a penalty, a performance penalty, right, with heavy use of defer. That is now less so. I don't know if it's completely sort of a non-issue anymore, but defer is much faster. So Rob, when you say that, hey, you should just lock and then defer the unlocked, I'm like, yes, now I would totally jump on that bandwagon.
Yeah, now it's almost impossible to measure the amount of time that it takes. If you have a single deferred statement in a function and you measure it, you're going to get flakes. Sometimes you're going to get the defer is faster because it's so impossible to measure nowadays.
Isn't it just optimized out though in that case? Because if it's just a defer in the body of a normal function and not in some kind of loop, if it's in a for loop, then of course you'd have to wait for runtime before you can know what's going to be deferred. But you could look just by static analysis, you could probably look at a function and say, well, I can see the exit points, so I'll go and call the methods, whatever they are, in those places. I don't know if that's what it's doing or if they've optimized the entire mechanism.
So it wasn't that easy because of panics. So you might see the returns, but you would also need to check all the statements that can panic because you need to run the defer statements on panic. And also loops can be unwound. So you can actually start deferring like 5 or 6 of the statements that you're going to defer anyways. So there is a lot of dark magic in the compiler. And I think this is one of the funniest ones to read.
I just read that if you don't recover, there is additional performance penalty. Maybe it's because like they're doing some optimizations. But if you have to like recover, then it becomes a more of like a hairy issue. Maybe I don't know how it works, but
But for readability, of course, defer wins hands down. I mean, when you open a file and you check the error, and then you say, okay, defer, file, close. You've got everything to do with opening and closing files in the same place. And it's quite obvious as well to notice when you've forgotten to close things because you're looking in that same area. It's right near where you've opened it. So I think for readability, it just wins hands down, doesn't it?
The typical sort of guidance I hear from experienced developers like yourselves is basically, hey, use defer because readability and because you don't want to forget, right, to leave like a file handle like open or something like that, right? That's just resource misuse. But I would say sometimes I've done it both ways, right? And yes, I have a penchant towards defer, but at the same time, depending on how big the function that I'm working with is, how much I'm doing in there, I may choose to, if I open a file, I may choose to, have the 2 or 3 extra lines that I'm doing after, I open the file and then explicitly close, the file, like without using defer. So I think, it's yes, generally speaking, you do want to use defer, but I don't think it should be interpreted as gospel.
That's true. It really depends on the job. Like in some instrumentation libraries, we specifically didn't want to, use defer. But if I have like more than like 10 microseconds of work to do or whatever, like I don't care. I would just defer it.
Yeah, of course, the other benefit is if you defer, then it doesn't matter where you exit in your function. That's the only thing that's worth saying. So if you're opening a few files and you're going to do a few more things a bit more complicated, then it definitely helps. But yeah, I think with everything, it kind of depends probably on each individual case, unfortunately. But
it depends. That's our patron saint for everything.
Yeah.
Yeah. It's true, though.
So what about concurrency?
Oh, yeah. I told you we could do a whole episode on defer.
Yeah, no, I'm sure of that. Yeah.
Yeah.
Actually, when you told me about defer, I said that together with defer, we should talk about select. Because it's, I think, beautiful. Because most people say that Go channels are great. But a channel, after all, is just a queue with a mutex on top. Select, on the other hand, is so hard to implement. I think select is the real beauty there.
It's funny because it seems really simple from the outside when you just think, okay, yeah, there's a few events that can occur. I'm going to put each one as a case. It really feels quite simple. And it's really powerful as well.
Yeah, but that's kind of the beauty of Go.
Yeah, right.
I think the main concurrency feature in Go is the select statement than anything else. It's like where the magic happens and it looks really simple to you, but like that's literally just impossible. It's so complicated to implement.
I want to dig into that a little bit. So I've seen several codes where you have a select statement and you have a number of different cases. Sometimes you have a default, sometimes you do not. Can somebody explain why that is, and what is the impact of having a default case in your select statement as opposed to not having one?
So select is used to receive and send from and to channels, and select blocks until one of the cases becomes available. If you have a default case, most like a switch. So basically, if nothing else is available, select will just continue. Yeah, it takes a while to get used to, because I've seen people like doing stuff in a loop and having a default case in there, and they were just spinning, trying to get some work, and then, well, work is not available, let's do another round. While instead they should have just blocked. And in other cases, people checking for context cancellation without a default case, and they would just block everything, and that was hard to debug because, I mean, HTTP handlers, it doesn't detect that there is a deadlock and stuff like that. So yeah, default non-blocking, no default blocking. The best way to block a program from continuing is having an empty select.
Yeah. Which is useful sometimes. Sometimes you do want to have a program that just runs forever without consuming all the whatever it does in a for loop. Because even a for loop's doing more work than just blocking at a select, right?
Yeah, and actually what I found beautiful is that if you look in the runtime sources, the runtime builds a dependency graph. So like when a goroutine becomes available to do some work, the runtime knows, okay, that's the next one to schedule. If you have an empty select, that's one way to communicate to the runtime, this is never going to be ready. And so the runtime doesn't just handle it anymore. Just ends somewhere and it's going to stay there.
So an empty select is like a humane way of saying, I want this program to just stop, but it's not really, that all my goroutines have gone to sleep. I literally want everything to just stop.
You just want the current goroutine to just hang, right? Like everything else is going to work.
Yeah, if you have a main program and you've kicked off 5 threads and the threads are going to do all the work continuously in your program, I could see a case then for having an empty select on that main thread, maybe. Although if you think about context, and you can trap the signal from a control C and cancel a context from that. Mm-hmm. And if you do that, then you're actually able to tear down gracefully from a command C, and then you can also there's a way to write it so that the second hit, the second signal that comes in actually kills the program. And so that's quite a nice little pattern, things like that.
Yeah, just have a channel that is one big. This is very nice.
Yeah, a buffered channel with one space for one thing.
This episode is brought to you by GoCD. With native integrations for Kubernetes and a Helm chart to quickly get started, GoCD is an easy choice for cloud-native teams. With GoCD running on Kubernetes, you define your build workflow and let GoCD provision and scale build infrastructure on the fly for you. GoCD installs as a Kubernetes native application, which allows for ease of operations, easily upgrade and maintain GoCD using Helm, scale your build infrastructure elastically with a new Elastic agent that uses Kubernetes conventions to dynamically scale GoCD agents. GoCD also has first-class integration with Docker registries, easily compose, track, and visualize deployments on Kubernetes. Learn more and get started at gocd.org/Kubernetes. Again, gocd.org/Kubernetes.
You know, when you do these signal channels, these channels where you don't plan on sending any information, only really you want to send a signal of some event, like I've finished or something like that. What type do you use?
Ooh.
Do you have a favorite? Because I have a favorite. It's a loaded question. I just want to tell you what my favorite is. So if we could just get through yours.
For a moment, I thought you were going for buffer channels. And I was like, ooh, that's a loaded question. But you found a better one.
Okay, so one of the, I guess, the idioms that have sort of been floating around is use the empty struct, right, as sort of a messaging mechanism, because it really occupies no memory. Nothing's been allocated. Basically, you're just signaling, right, just a pure signal. Beginners might also be tempted to use booleans. I've seen integer types. I've seen people passing over channels. I've even seen errors being passed as a signaling mechanism over channels. I'm not going to say that these mechanisms are wrong. Sometimes the value that you receive from that signal, basically you treat it as both a signal and a value for you to do something with, and it's going to depend on your case, obviously. But typically, if you want a sort of a zero allocation type of mechanism, you're just sending a signal. Then the empty struct is your friend.
It's also, I think, worth to mention that it really depends. If this is going to be a public API, for example, like the signal package, or where you will have like different events and so on, I think it makes sense to have your type. You can have like a type for the signals, and you can have maybe more like predefined signals exported from that package and so on. But if it's more of like a self-contained thing, it's totally just good to just have an empty struct.
Yeah, the nice thing about the empty struct is you can't put any information in there. So it really just makes that very clear that what it's going to be used for. I've seen a bool used as well, and I just never know if it matters if I send true or false down there. Like if I feel like there's some API now, whereas with an empty struct, it can't be anything other than just a signal. So I like to use it that it's kind of a signal to programmers too. Helps with glanceability.
And sending false, I mean...
Is it the zero value?
But yeah, Boolean is dangerous.
Yeah.
Because if you get true, there was a signal. But if you get false...
you don't know.
That's the geekiest bit we've ever had on GoTime while I've been on.
I know, right? And I think we all smiled at the same time. We knew exactly where you were going with that.
Yeah. That's it. We need more bits like that.
I mean, most of what I do right now is code review. I read way more code than I write. And when I see people using like a map of something to bool, I always ask, what if you get false, but the key is in there? Same for channels. What are you trying to tell your users? Or like buffer channels of size 50. Well, I mean, I can understand 1 or 2, but when it starts being like 100, I need a comment to tell me why.
Yeah.
Treating it like a queue.
Probably there's some performance tuning or something going on, but you're right. It just gets hidden and it looks strange, and no one will touch it. Like you'll be scared to go near it because you feel like, well, why is it 50? It's a bit like those numbers on Lost when they just didn't know why they were putting the numbers in. You just can't stop doing it just in case.
So let's talk about concurrency as they are used in things like libraries, right? So there's an idiomatic way of actually using concurrency in your library, basically hiding that completely away from the user of your library. And there's also guidance that basically says, allow the user of your package, of your library, right, to do things, to orchestrate concurrency, right, using your package. You can do things sort of asynchronously, like, or rather top down, right, without, basically having sort of a crossing that boundary, so to speak, right? So if you're going to do concurrency, do it internally, right, neatly inside of your package. But any other case, you should let the user of your package orchestrate concurrency around there. And if there is a chance that you're going to be doing things concurrently, your library should accept, right, a channel upon which for it to send back some, a signal or some result, right, of having done the concurrent work for you. So I've seen basically, advice all across the board there. I'm interested in your take on that.
I don't like APIs that are asynchronous by definition. Every time I see a library that, for example, takes a channel and is going to send results over that channel, or even worse, you call a function and you get a channel back. I'm not a big fan of that because I always have to read the code. For example, if I cancel the context, if they take a context, and are they going to check for cancellation at every send, or do I need to drain the channel? Will they block if the channel fills up? All these kind of questions. I prefer when my libraries stay synchronous. I don't like promises.
I completely agree with this. I think everything should be blocking as much as possible. And because it's so easy to orchestrate everything with Go, I totally see that like it's more valuable to give that also precise, I think, control to the user.
Mm-hmm.
And some libraries end up actually like having two different APIs in the same package. They're kind of like, replicating the same API. And it's completely, I think, just unnecessary because it's easy to, orchestrate and put things together in Go. But one of the things that Go is like doing not properly is there is no easy way to, on the Go doc or anywhere to, carefully label things that, this is going to actually run in a different Go routine or whatever. For example, the HTTP package, every handler is running in a different Go routine. And you need to maybe leave a comment on the Go doc. But, there's not it's not really readable. Or some people just kind of miss it. And I think we need a better approach to maybe explain how the underlying, implementation kind of works from the perspective of concurrency. Sorry, I'm slightly changing the topic a bit.
No,
yeah.
I agree. I mean, one thing is like when you call a function that might spawn goroutines, but as long as it collects them before returning, that is fine. But if that stuff keeps running, or it's going to run, for example, your closure that you pass in another goroutine, you might want to know, for example, the file path walk function. You might want to know if that thing is going to be run concurrently. Because you might be closuring over a variable that you don't want to be touched across threads. Well, it doesn't. Spoiler, it's synchronous. But it would be nice to have a way to say, this is not going to require synchronization.
Yeah, in the beginnings of Go, I've seen a lot of people actually like having mutexes for some of the stuff that they were trying to, access from like several like closures, which was actually never the case because, the library was like given the guarantee that like one function will be, be executed at a time and so on. But there's like literally no way to, explain it other than just put in this information in the Go doc, and it's not very accessible.
Yeah, that's an interesting thing. It makes me think of something that always occurs to me, which is that concurrency, anytime you're writing concurrent code, it's best to keep it very local, keep it very nearby, all of it. And call out to functions to do other work. Don't try and do all the work so that the page kind of stretches down and you're left with bits of concurrent code scattered throughout. And also things like passing mutexes by pointers and things like this. If you can avoid that and just have a mutex in one place and do all the concurrency in one function, that's just so much easier to maintain and to reason about later. That's some experience has kind of taught me that now, and I tend to do that. I tend to have all my concurrent code in one place, and if it's a wait group and it's doing some work, I will call out to a function to go off and do the actual work, and allows all my concurrent code to be uncluttered from that.
I couldn't agree more.
So we've been deliberate, right, with our use of the word, concurrent, right? So one of the sort of the first things you learn in working with Go is that concurrency is not necessarily parallelism, right? So by having concurrent code, you allow, right, for the system that's going to be running your code to have your code run in parallel, but that's not something you can actually control. Maybe I think it was a talk by Rob Pike, actually titled as such, right? Concurrency is not parallelism. That sort of shed light on that whole mechanism. So is there been any case that you've encountered where parallelism wasn't the right thing to do? That you wish you didn't have a concurrent code that ended up being run in parallel, like any sort of races that you didn't anticipate or anything like that?
I had a big headache trying to figure out how to properly do init, because the code I was using was spawning goroutines and was blocking until those goroutines returned it. But during init time, you can't spawn goroutines. I mean, you can spawn them, but they won't run. So that code was deadlocking on startup.
Wow, that is a tough one.
Yeah,
never heard of that one before. That's wow. That's amazing.
Amazing is one word, yes.
But I mean, don't use init. If we don't use init, we might actually avoid problems like that.
Here. I second that motion.
Yes, do not use init. I agree.
Go ahead, JBD.
One of the things that I actually, I sometimes need parallelism, but not like any concurrent stuff, like such as I just want to be able to lock a Go routine to a processor, and I want to be able to, access everything without any locks or whatever. Go doesn't give me that like precise like level of control. So that's kind of funny. Like there's a lot of concurrencies related features, but if I just want to distribute some workload over some processors, and I know like the data affinity and everything, I can't really do it because there's absolutely no way to do it. So these are different problems, parallelism and concurrency, and it gives you like different advantages. So there's the thing that there's like literally no way to tweak things, which is a bit bothering sometimes. But I think it doesn't really represent the average user. But sometimes you kind of feel like you're sort of blocked.
Yeah, I mean, my experience is mostly I build a lot of web stuff, a lot of web APIs, that kind of thing, websites, even blogs, things like that. So I don't need to. I'm not going in there saying, "Oi, I want this Go routine on this core, and don't you move on to another one." I'm happy for them to get on with it, do what they need to do, just to render some bits. But yeah, so that is always the case, I guess, is those trade-offs, and whether you think they're worth it or not. That's really the judgment call you get to make about the language, I suppose.
If you consider if we start adding that type of like precise control, I think it's going to get super complicated, especially if libraries started to like tweak those arguments and so on. So I think I totally can see that it's benefiting the entire community to maybe, have more of like a simple API service, which is just the Go routines and some sort of like synchronization mechanisms and providing nothing else. And, it kind of also carves the community and the user base based on the, functionality you provide. So you are not going to maybe pick Go for some certain tasks because that the functionality is not there. If it becomes critical in the future, we can reconsider it. But maybe that's how things work. I don't know.
I was following a very long thread on GoNuts last year, I think. And at one point, someone suggested, and I think it was Ian Taylor, suggested to use the Unix package to call set affinity to lock to a specific. So I've seen code using that, like Unix syscalls. They're not cross-platform as we love Go, but if you go that deep, at a point, you might as well do your syscalls, as you would in C.
Yeah, that's what I do.
Ooh.
I like my OS thread and I, call into either that set affinity or NUMA type of stuff, unfortunately.
Oh, we need to, that needs to be a talk, doesn't it? We need to see that. Why on earth are you doing that and how? That's what we want to know.
My current job requires it because of some benchmarks and so on. So this is literal for fun type of projects. It's not some production service, or whatever, but those tools are available to you. That's true.
Interesting.
You might as well write in C.
I meant that as a joke. That is a joke, Yana. This was...
My life is a joke, man.
Wow. Oh.
I like being on the edge.
Bleeding and all.
There's another trick that I do which I find really useful. I'll try and describe it. It probably isn't the easiest thing to describe, but it's essentially sometimes you want to do lots of work. There's lots of work to get through, but you know that you can only or you should only really be doing, say, 5 at a time. So you're happy for it to run as fast as it can, but only do 5 at a time. And one simple way to achieve that in Go is to have a buffered channel, and the size of that buffer is the number of Go routines you allow concurrently, and then each Go routine tries to write something into that channel, and if it succeeds, it then unblocks, it goes ahead and it does its magic. And of course, the first 5 that'll be no problem. They'll all be able to write into the channel. The 6th one that comes along, suddenly this channel's full because they were all filled up by the other goroutines. So this one then has to wait, and he'll block until something is then released from the channel, and they get released when the task is finished. So it's a bit like the mutex where you lock and then defer the unlock. You'd actually write into the channel, and then in the defer, you read something out of the channel, freeing a space for another goroutine. So that pattern is quite easy, I think, to reason about if you know the basics of channel semantics and how to code that in Go. But actually it turns out to be quite powerful, and especially since that buffer can be configurable. So you could actually even make it a flag to the program to ask how many of these do you want to be able to run concurrently. Another way to do it, of course, is just to spin up a certain number of goroutines and just have them drawing from a queue a different way. But I find that to be a little bit more confusing, because you then have to have, in another goroutine, you have to be then populating the work in some way, and that feels a little bit strange. But that's one little pattern I've found that I quite like.
I really like that. And I really like how Go is so simple that you can actually implement a semaphore in 3 lines. Because what you described is usually a semaphore. And channels are such a higher level primitive that they allow you to implement whatever you want. I mean, even if you need a mutex with a try lock method, because you want to try acquire, and if you can't manage, well, just retry in a bit. Well, you can do that with a channel with a select and empty default block. I mean, channels are so much more expressive than just mutexes.
Yeah. And you remind me as well of the time.after that you can get in the time package, which actually returns a channel which sends the time on it after a certain duration. So you can use that in select blocks as well to say, right, we're going to wait for this, maybe this goroutine to finish. If it hasn't finished within 1 second, we'll run a different case. We might update the stats or something. We might present an update to the user. So every second they get an update while we're waiting. Once the chat task then finishes, of course, the other case will trigger and it'll go and do the other thing. And there's also a ticker that you can do as well. But time after tends to be quite nice. Nice way to express timeouts in test code as well. If you're waiting for test code to complete, it's nice to have that little timeouts in there as well.
I've had bad experiences with a time package.
In general?
Yeah.
It sounds like a one-man show on Broadway. Roberto Clapis.
I've had trouble with the time package.
The time package monologue.
Yeah, exactly.
I really found myself writing a flowchart on paper to understand what functions, what methods I could call on a timer, on a ticker, and in which case. Because like stop, or like do you have to drain after stop? And if you do, and all that kind of stuff. So it's a nice package, but use it carefully.
Sage advice. Sage advice indeed. And that leads us neatly to the end of our show today. Thank you very much to our guests and co-panelists, Johnny Borsico, Jana Bidogan, and Roberto Clapis. Nice to hang out with you. Thanks very much.
Thank you.
We'll see you next time. Oh, it's not your time to talk now, Roberto. I'm doing the closing bits. We'll see you next time on Go Time.
All right, thank you for tuning into this week's episode of Go Time. If you're not yet, hang with us in Go for Slack. We have a channel called Go Time FM. Look it up, you'll find us. Hang with us during the live shows, connect with other members of the community, share stories, share code, share coffee recipes, whatever. It's a lot of fun. Also, we have discussions at changelog.com on every episode. Head to changelog.com/GoTime, find this episode, and discuss it with the community. Also, thanks to Fastly, our bandwidth partner, Rollbar for helping us move fast and fix things, and Linode for hosting the Changelog platform. Our music is produced by the mysterious Breakmaster Cylinder. And if you want to hear more awesome podcasts like this, subscribe to our master feed. It's one feed to rule them all, plus some extras that only hit the master feed. Head to changelog.com/master or search for Changelog Master in your podcast client. You'll find us. Thanks for tuning in. We'll see you next week.